Now, if we see the power trend of, if you look in the graph, then you would see at this point, till this point, the clock rate and the increase in the power, they are both increasing. But at certain time, around let's say in 2002, from 2002, use of power started to drop considerably. This is because we cannot use more power, because it is going to generate heat, and we do not have a heat sink that can absorb more heat if we go beyond this line. Now, the power equation, if you look carefully, then over the last around 20 years, from here, from this part, from here to around this part, around this 20 years, you would see the power increases 30 times. From this and voltage actually decreased. It started with 5 volt, now gradually is decreased to 1 volt, and the clock rate increased almost 1000 times. So the power equation is capacitive load, voltage square, and frequency. Now capacitive load is the uh, capacitance of both transistor and the communicating link. The function of the capacitance of the transistor and the communication link. So let's use this power equation in the next slide. So suppose we are trying to design a new CPU where 85% of the capacitive load in the new system will reduce the capacitive load by 15%. It will have 85% capacitive load then compared to the old CPU, and voltage use reduced by 15%, and frequency is reduced by 15%. So if we compare this, that would give us this result, which means the new system can be, if we just decrease the capacitive load just by 15% and voltage and frequency by 15%, then the new system would use 50% less power than the previous one. So what is power wall? Power wall is we can't reduce the voltage further. We are almost at the end. We cannot reduce it further, and we can't remove more heat, which means we cannot design or build heat sinker that can absorb more heat than it is doing now. So this diagram, you can see in this diagram that it shows the uniprocessor performance of the uniprocessor system. Now around this part, if you look here, around this part, the processor performance increased 25% per year, but around this part, see, the processor performance increased 52% per year. Now again, around this part, processor performance only increased 22%, because since this is single processor uniprocessor system, so number of transistors that you could accommodate on the single area were like almost at the limit. That's why the performance was increasing, but not like this where it was increasing 52%. It was increased, but less than what it used to be. So this was the uniprocessor performance graph. Now multiprocessor. So from uniprocessor we moved into the multiprocessor system, which means it's multi-core microprocessor where more than one cores are there. We started with 2 cores, and now we have more than 2 cores. It's 8 core or so. But what this has given us, it requires more complex parallel programming, which is not very easy, if I can say that. Hardware executes multiple instructions at once, hidden from the programmer. as programmer, we wouldn't be able to identify that more than one instructions are executing at a time, but it is as we have seen in the early stage of this slide, that abstraction, it is abstracted from the user that the more than one instructions are running at a time. Hard to do. What is hard to do? Programming for the performance, load balancing, optimizing communication and synchronization. So programming for the performance means we need to consider the number of cores and how we would like a program for multiple cores, and then load balancing. All the cores should be utilized most of the time, and then optimizing communication and synchronization. That means when the core needs to communicate or dependency, these are the things that are really hard. Okay, now spec CPU benchmark. This is just a benchmark from standard performance evaluation corporation. So it's like it generates an arithmetic mean. This is in the next slide. We'll see here we have a set of 12 integer benchmark. We also have 17 floating point benchmark, which is not shown here, but here we have 12 integer benchmarks, which are these 12 integer benchmarks, and based on instruction count and CPI and all these thing, they figured out an arithmetic mean. This is the arithmetic mean. So the larger this value, the better the performance of the system. So this is what the spec performance means actually. Spec benchmark performance benchmarking means. Now Amdahl's law. So what is Amdahl's law? If I explain it rather than improving, rather than discussing what is written here, very generally, what Amdahl's law says, that if we improve some part of our system, then the performance improvement will depend on how much we are using that improved performance. So now see what it says. Improving an aspect of a computer, and expecting a potential improvement in overall performance. Let's say you have bought a new graphics card or GPU, or you installed a new GPU in your system. Now after installing that, or after having that GPU in your system, you'd expect to improve the performance of your system, but you can only see the improvement when you are doing some high-end graphics work, or you are using that GPU. If you are not using that GPU in your processing or in your work, then you wouldn't find the difference. So it is not that you installed a new hardware, high performance hardware, and automatically your system will give you improved performance. You need to use that improved a new hardware to see the performance improvement. So the equation for Amdahl's law is T improved equal to T affected, how much that improvement affects the overall performance over improvement factor, and then there will be some portion which will be unaffected. For example, let's say we are trying to do a multiplication, and it takes around 100 seconds, and from that 100 seconds, just multiplication requires 80 seconds. So how much improvement in multiply performance to get 5 times overall performance? So how much improvement do we need to do in the hardware so that we could get 5 times the performance? So 5 times performance means we are having 100 seconds for this multiplication. We require 100 seconds for, as it is shown here, we require 100 seconds for this multiplication. Now what we are targeting, we are targeting 5x overall improvement. That means we'd like to execute this multiplication in 20 seconds. So to achieve that, what improvement do we need to do? So improvement, would like to have it in 20 seconds. Affected where the multiplication, this part, because the rest, that means the 20-second is unaffected, it will be unaffected. So this is our 80 seconds, and n will decide what improvement we need to do. And then we have 20. As you know that this one is this and this gone, so we cannot achieve that performance. That means we, with the current setup, we cannot achieve 5 times increase in the overall performance. Another one, performance matrix. So MIPS, millions of instruction per second. What it means? A measurement of number of program execution speed based on the number of millions of instructions. This just a straightforward equation. MIPS is equal to instruction count over execution time into 10 to the power 6. And if we do this calculation and simplification, then MIPS would become clock rate over CPI into 10 to the power 6. CPI varies between program on a given CPU. So CPI varies between programs just because of the number of instructions and so on.